All right, so let's go back to the practice problems. And let's start with the practice final just because that's the closest one. So y'all wanted to cover 26 and 23. If you have any other questions about the practice final that you want to go over, please type them all in the chat just so we can go through them all hopefully now. If we have to go back to it later, that's completely fine as well. But okay, DealsAlder. So we are going to go over DealsAlder because someone requested that, but let's just look at this guy first. So this is going to be a retrosynthesis question because we have our final product and we're going backwards. And the first thing we have to note is we have a bridge, right? Excuse me. And in the bridgehead, we have how many carbons? I circled it already, but yes, we have one carbon in the bridgehead. And that means that we had to have what kind of ring in our starting material? How many members? A pentene or a 5-membered ring. That was ugly. All right. That was ugly too, but whatever. We're dealing with it. And we have our 2 CH3s. And so we have this double bond here in the final product. And so we know that this double bond ends up in the middle of where the 2 double bonds used to be. So in the diene, we had this. And in the final product, this double bond is in between where the diene was. And the dienophyl is just going to be whatever is left over here. So in this case, was our dienophyl a double bond or a triple bond? What do we think? A double bond. And the reason we know it was not a triple bond is because if it was a triple bond, we would still have one more bond here. But since we don't, we know it was a double bond. So between our answer choices, what has to be correct? C, and I agree with you. Any questions on how we got this? And remember, there are no dumb questions. Never be sorry for asking questions. But I'm here for. I'll never get upset or judge you for asking a question or not knowing something. All that good stuff. I'd rather you get it wrong with me than get it wrong on the exam. So again, if you have questions, please ask. But we're going to go on to number 26 in the meantime. So, of all of the reactions that we have learned about this semester, which one are we doing here? A reduction. A reduction. Sweet. And how do we know it's a reduction? What gave it away? This is our strong reducing agent. Sweet. And so remind me, what is our reducing species? What is doing the reducing here? H minus. Perfect. Okay. Cool. Making sure you guys remember. So when we attack here, we have a ketone. So we don't have any kind of leaving group to get rid of. So that means what kind of alcohol do we end up making? Primary, secondary, tertiary, what do y'all think? Secondary. Ketone always gives you a secondary alcohol. Cool. So we can automatically, well, we can't really get rid of anything yet. because they all have our CH3 and hydrogen here, so we're good. So we have to go on to this carbon, right? Because this is a chiral center, and so he'll try to trick you by swapping that up, right? But we never touched this center. We never did anything. There's no reaction happening there. So we have to maintain the same stereochemistry we started with. So this flipped it. This flipped it. Those two are wrong. And so between 1 and 2, can we pick, or between 1 and 3, can we pick which one is more correct than the other? No, because this is planar. We can either end up with this one or this one. So B is the correct answer. Number 1 and 3 will be made in a mixture. I feel like I explained that a little bit weird. Did that make sense to you guys, or do you want me to run through it one more time super quick? Made sense? Okay, sweet. Alrighty. So I'll keep this up for a second. Do you guys have any more questions that you would like to go over in the practice final? No? Okay, cool. So let's move on to the chapter 17, 18 question. Okay, so to the person who wanted the chapter 17, 18 practice problems, which packet did you want? Because there's this packet or there's the other one. So if this is the wrong one, let me know. I think it's the one with the answers. Okay, this one has the answers, so I think we're good. And you wanted number 68. And I will erase all the writing. Is this the one you wanted to do? Yes, okay, perfect. All right. So, first of all, which kind of reaction do we have? And I don't know why that this is like this, but it's supposed to be PBr3. Or PCl3, my bad. So, okay. People were saying, like, I know it's a halogenation, but what is the P doing there? Yeah, it's supposed to be a PCl3. I don't know why it just said P. So now that we know what the P means, what kind of reaction are we doing? What do we think? This is the one with the complicated name. If you can give me even like a piece of it or a general gist of what it might be called. HV something. Exactly. Good enough for me. It's the Volhard Zielinski, and I 100% spelled something there wrong. So, it's okay. So, for this reaction, we know that PCl3 is going to do what? OH2Cl. Absolutely. Cl2 does what? Or it adds a chlorine to where, I should say. To the alpha carbon, absolutely. And so what does H2O do? Adds on the OH, exactly. So what kind of mechanism does it use to add the OH? The nucleophilic something. So once we do the first two steps and we get here, what kind of mechanism do we use with H2O? If you guys don't remember, that's completely okay. We can run through it real quick. So, remind me, how stable is an acid chloride? Super stable, not very stable, really yucky. What do we think? Not stable at all. It's the least stable. It's the most reactive. We don't like it. So H2O is going to come in. Oopsie, too many. It's going to attack here. It's going to kick that off. So we end up with this. And now the Cl- that we have left over can come and take that hydrogen back. So we end up with this. So this last part that we did right here, what kind of mechanism was it? A nucleophilic what? And okay, so yes, so that was a nucleophilic acyl substitution. So we replace the Br with an OH. And yes, exactly. If we were given the same first step with no H2O, we would finish with this product. But since we were given H2O, we get this product. And so that would be, which of the following answers correspond to what we drew? This one. Ta-da! So any questions about this one? Awesome. You are very welcome. Okay, so I think those were all the ones that you guys wanted to cover specifically. I'll give you guys a minute to send me any specific problems that you have. If nothing else, people wanted to go over DealsAlder really quick and the ester synthesis reactions. But I'll give you like 1 minute before we move on. I'll take a sip of my aboba. So awkwardly quiet online. Like, I know you guys need breaks, but it feels so uncomfortable. Like, I'm just sitting here staring at the screen. Okay, so it's been almost a minute. Let's... All right, so... go back on here. And let's go to DealsAlder. All right, so DealsAlder is essentially a reaction where we have a diene and a dienophile, and it is a concerted reaction, which just means all of these arrows happen at the same time, all the bonds are broken and created at the same time, and we finish with something that looks like so. We made a ring, right? And so the diene is any conjugated diene. That's the nucleophile. It has to be an S-cis conformation, and it wants electron donating groups. The dienophile can be any double or triple bond. It's the electrophile. It maintains its configuration, and it wants electron withdrawing groups. And I'm not going to go over all the groups again because I've given you guys this table. So let's do some examples. No, I hate that. Okay. Okay, are you like this? Okay, there we go. So let's say we have this diene, right? And we're going to react it with that. So we are going to number this 1, 2, 3, 4, and this time the numbering actually does matter. So we want 1 and 4 to be on the open side. So think of it as like the alligator that we talked about before. You want the chomping side open so that it can chomp here. So you want the mouth open so it can chomp the dienophile, right? And we want 1 on top, 4 on the bottom. It doesn't really matter. Like in this case, it's symmetrical. So if this was, it doesn't matter which one is the top and which one is the bottom. In other classes and when you go on in chemistry, that will matter, but it doesn't here. Same for the dienophile. So A and B. Doesn't really matter which is which. Just do it the way they give it to you. And so we connect 1 to A, and we connect 4 to B, and we go around in a circle like so. And so what happens is we still have this skeleton left over, and we still have this left over, right? And now we broke this double bond, we got rid of it, and we made this new bond here. Same thing with this bond. And we created a double bond here. So we made a 6-membered ring, and we made a double bond in between the double bonds of the original diene. A more complicated one that you guys should know, we already saw the 1 carbon in the bridgehead. So let's see what happens when we have 2 carbons in the bridgehead. And we'll use the same dienophile just for simplicity purposes. Actually, I want to make a second point, so we'll do that. All right, so 1, 2, 3, 4, A, B. Let's connect the ones we know. Make the circle of arrows. All right, so what happens to these 2 carbons? What do y'all think? It becomes a bridge, exactly. So there's 2 carbons in the bridgehead, so that looks like so. And I'm drawing it flat, and then I will also draw it in 3D. So we also made a double bond right here. And we have our two substituents, right? And now we actually have to decide where these will be pointing, whether they'll be pointing up or down. So first, we know that they have to point the same direction because this double bond is cis. So these have to be cis. Is there any way to tell if they will be wedged or dashed? What do y'all think? Is there any way to tell whether those substituents will be wedged or dashed? Brave guess. Thank you for responding. It's okay if you don't know. They guessed no. And that's what I would say too, right? Because this is flat and they can either be wedged or dashed. So we can make both of the products, but even though we form both products, one of them is going to be more favorable. So let's go ahead and draw them if they were wedged, aka pointing up, versus if they were dashed, aka pointing down. So this is wedged, this is dashed. And someone used a really key vocab word, which is the endo and the exo product. So which of these is endo? Is it the wedged or the dashed one? Dashed, exactly. So here we have endo and exo. And which of these is preferred? So there's a little bit of, there's like 50-50. And the endo one is preferred. And the reason is, one, this interferes with the bridgehead. We don't want them pointing up in the way of the bridgehead. And two, here these double bonds can interact with this double bond and it becomes more stable. So this is going to be our favorable product. So almost every single time we prefer endo over exo. There is one example where we prefer exo, but I'm not going to bother with that because Dr. West said he won't test you on that. Cool. Any questions? Okay, so someone asked a question, and I think I understand what you meant, but if I don't answer your question, let me know. So the reason these two are going to be pointing the same direction, so both wedged or both dashed, is because the dienophile was cis. So both of these are pointing on the same side of the double bond. If they were trans, so pointing opposite sides, one would be wedged, one would be dashed. We wouldn't have a exo or endo product. Okay, cool. Alrighty. So to the person who requested DealsAlder, does this make a little bit more sense? Are you happy with this? Or do you have any other questions? Okay, sweet. I swear I just heard someone singing and I was like, I'm going crazy. I've lost it. Okay. Anywhoomst, let's go down. Oh no, where's chapter 18? I have to add that. My bad. Let's go to a different handout. All right, perfect. So we're going to do this reaction. I'm just going to do it on a new page. Actually, let's go through it with it already drawn out because that might be better. So the acetoacetic ester synthesis is essentially when we have a beta keto ester and we have 3 different steps. So in the first step, we have a base and an alkyl halide, which means we're doing an alkylation. In the second step, we have NaOH and H2O, which is a nucleophilic acyl substitution. And then heat is just a decarboxylation. And so before we go into detail, someone asked how would he ask these questions? Probably literally just like this. He would just give you this and say, what is the final product? So you're expected to know that in the first step, you are alkylating the alpha carbon. So that is shown right here, and you end up adding the alkyl group to the alpha carbon. In the second step, we do a nucleophilic substitution. So we take this leaving group and we replace it with an OH. And then we do a decarboxylation. So decarboxylation, in the first step, we're going to rotate this bond so that the OH is pointing in the same direction as this ketone. And just like DealsAlder, we're going to have a concerted reaction where all these steps are happening at the same time. And we essentially break away this as CO2 and it goes away. And we end up making the enol, which can then tautomerize with the ketone form. And then someone said, I was confused with that enolate there. So this one. All right. So essentially, the only reason that's drawn there is because when we were talking about it in SI, people were a little bit confused about like what this is. And so essentially, when you take the hydrogen off of the alpha carbon and you have a negative charge, that intermediate is considered the enolate, right? And so we know that the enolate has 2 different forms or 2 different resonance structures. So this drawing is just the other resonance structure of the enolate. So these are the exact same thing. I just didn't want you guys to forget that this also exists. We just don't tend to draw it out. You're very welcome. And then the malonic ester synthesis is essentially the same exact thing. So I will zoom out so you guys can see both of them. And then let me know if you have any questions on this or anything like that. I believe there was a couple good questions in the practice problems about these 2 reactions, so I can look at that real quick and we can do one of them if you guys would like. So yes, the acetoacetic ester and the malonic ester are both beta to one another, which just means the carbonyls are beta to one another. When we do the alkylation, we take an alpha hydrogen, but in the last step for the decarboxylation, the 2 carbonyls are going to be beta to one another. Let me know if I didn't exactly answer your question. And yes, we can do a problem. Let me just make sure. Okay. So let's go back into here. So here's an example. Almost the same thing, or exactly the same thing we just did, right? So he could ask it to you this way, where he literally just gives you the reaction sequence and he asks you for the answer. Or he could do it like, is that really all he gave you guys? Okay, this is a good one. All right, so this one is very similar. It just looks kind of different. So it is the malonic ester synthesis. And in this one, he already gives you the final answer. He just wants the intermediate. So let me just add back in the work that I had already drawn, just to make it easier. Ta-da. All right. It does look scary. I know, it's so ugly. And honestly, I think that's the worst part of the final, that everything looks kind of gross and you have to like figure out what's what. Like when I took it, to be completely honest, I got so overwhelmed in the first 10 minutes that I like flipped out. Don't do that though. Try to like calm down, breathe. And it looks really scary at first, but when you actually look at it and figure out what it's asking you, it's not too bad. And that's how he gets you, by making you think it's scary before you actually try it. So for this one, it looks super, super overwhelming, but if you really look at it, all it's asking for is, in the alkylation step, what was Y? So what was the alkyl halide, right? Excuse me. This one's asking for Z, but there's another question that also asks you what Y is. So if he asks you for Y, all you have to do is go to the final product, right? And just look at what the alkyl group that was added is, and that is your Y. If he asks for Z, all you're going to do is take Y, which is the alkyl group, and add it to the alpha carbon right here. So you just take that hydrogen, get a negative charge, and add the R group. And so that corresponds to B. Make sense, or is it still kind of scary? Or does it look a little bit less overwhelming than when you first looked at it? Hopefully it's just a teeny tiny bit better at least. So when you're doing practice problems, just keep doing it over and over until it looks less scary, is what I would recommend. And KOTBU is just, start right here. So K is just a spectator ion with a plus, so we know the oxygen has a minus. T is going to be a tosylate. So that's just going to be, we'll just leave that as a T. And then the BU just means that we have a, oh wait, hold on. I lied. If it's OT with the dash BU, that just means tert butyl. And so that means the oxygen is attached to this. If it says OTS, this stands for tosylate. So I'm sorry I messed that up for a second, but hopefully that's better. And so what tert-butyl, or the tert-butoxide here, is standing for is essentially it's just a base. And then someone had asked a question about LDA. I wasn't ignoring you. I just wanted to wait till we were done with this question. And so basically, LDA can be used in most of the reactions we've done before. All it is a base, but it is a bulky base, which means that in the case of a halogenation, we are going to use the less favorable side. So let me actually find the reaction where we did this. I think it was here. Yes, okay. So we can either do an alkylation or a halogenation or anything. Usually you're going to see it in an alkylation. So we have alpha 1 and alpha 2, and usually we know that we are going to take a hydrogen from the most substituted alpha position. But if we have LDA, which is this right here, it's so bulky that you have to take the less favorable hydrogen because you want the least steric hindrance. And in that case, we add our alkyl group to the least sterically hindered side. Make sense-ish? Okay, you are very welcome. Okay, so it's 2:34. We still have some time. I think I covered all the stuff you guys had already put in the chat, so that means it's attendance time. If you did the attendance for the first hour, please go ahead and do it again for the second hour. I know it's annoying, but you have to do it twice. If you were here for both hours but haven't done it yet, please do it twice. And if you were not here for the second hour and are doing it for the first time, please go ahead and do that. And then once you get that done, please let me know what else you would like to cover. And if you had already asked a question and I missed it, I apologize. Let me know. So someone asked, tomorrow will you guys do questions too? So tomorrow we have our final exam review and we also have tutoring hours. So during tutoring hours, I will cover whatever you guys want to do. For our exam review session, we are currently in the process of making a big packet of a bunch of practice problems, some of which you guys don't have. So yes, we will be doing that. As far as in tutoring, I will have that packet. So if you guys just want to do that during tutoring, we can also do that. Let me know. You're very welcome. And yeah, I feel like the chapter 17 and 18 packet was not a lot of questions at all. So I totally understand where you're coming from. And chapter 18 is a big bulk of the exam. So we're definitely going to do a bunch of practice problems. You guys want to work on some chapter 17 and 18 practice problems now? Yes? Okay, cool. Okay. So let's go back to... Do you ever just have so many things that you just like get overwhelmed and you're like, I'm not even reading words right now? All right. Let's start with the chapter 18 questions that were in here, just to see what Dr. West has for you. So, we already did 59, so we're going to move up and do this one. We did this one as well. I lied. Okay. So, for 57, Br2 and H3O plus. What kind of reaction is that? No random P this time. Halogenation, exactly. And so when we perform a halogenation, does it matter if we have acid or base? Like, does it matter which one we use? Yes. Yes, it does. Cool. Okay, so when we have acid, how many times are we going to perform the halogenation? Once. One time max. Right. And we are going to add it to what carbon? We're going to add the halogen to which carbon, I should say. Alpha. Cool. So with these answer choices, some of them are real silly, right? Because what the heck are you doing here? What the heck are you doing here? That's not the alpha position. Also, even sillier than that, what the heck happened here? Right? Like, what in the world is that? So A is the only one that makes sense. Cool. Good. Any questions? Good. Okay. So, for this one, what kind of reaction is this? Very similar to the last one we did. It's a halogenation, but now with base, yes. And so with base, how many times are we going to do the reaction? Okay, so someone said reacts twice. So usually that is the case, yes. But I want you to be careful when you say that because it depends on the number of hydrogens. So as a general rule, for the halogenation in base, you're going to do it as many times as you have alpha hydrogens. So in this case, we only have one alpha hydrogen. So it's almost like he's trying to trick us, right? Even though it's in base, we can only do this reaction one time because we only have one alpha hydrogen. So we would get this. Or, my bad, it's Cl this time, not Br. So which one of these answer choices do we like? Two. I like that one as well. So let's go ahead and highlight this. This one is too far away. This one is an OH. Like, what the heck is that about? This one is too far away. And this one got rid of the carbonyl. So 2 is the only one that makes sense at the moment. Any questions on this one? Do we feel okay? So someone said, can we do 26? It's on the page right before this one. You meant 26? Are you on the chapter 17-18 practice problems, or are you in the practice final? Because if it's in a weird order, you're probably in the practice problem. Okay, cool. No need to be sorry. I just want to make sure we're on the same page. So let's go to 26. I really, this being out of order gives me such, you might be in the other packet, so let me go to that. The one without answers. Okay, cool. Let's go through that. I should have that downloaded, but I couldn't find it earlier when I was looking for it, so we're just going to go ahead and get it. All right. This one, correct? Yes. Okay, cool. So okay, so we can do this one, but I have a little asterisk for you. So all right, I have that one drawn out. That's why I came back here. So, which of them is most likely to be in the enol form? So, we used to say that B was the correct answer, right? Because they are beta to one another. They have the super acidic hydrogens in the middle. So we like that one. In addition, when it's in the enol form, we actually can have, that's so ugly, I can't handle it. We have one double bond and we have one OH, right? And when they're beta to one another and you have an OH, what's the type of bonding that can happen here? Starts with an H. Hydrogen bonding, yes, which is intermolecular, correct. So this type of hydrogen bonding makes it even more stable, right? The only reason I don't cover this question anymore is because a couple semesters ago, Dr. West said that this one was the answer, and I don't know why he changed his mind, or like what happened. So I would say that this is correct. But yeah, Dr. West said don't cover this one anymore. So my guess is he's not going to ask you about it. I know that's so weird to say, but I hope that was sort of kind of helpful at least. All right, so let's go back in here and let's just do like one more question. All right, so which of the following can undergo racemization in base? So what do we need in order to do a racemization? You need a hydrogen and a chiral center, but where specifically? On the alpha position, exactly. So you need to have a chiral alpha carbon, and you need to have a hydrogen present there. So which of these has a chiral alpha carbon with a hydrogen? C, aka number 3. And the reason the other two are wrong is because this one is not chiral, and this one does not have a hydrogen. So C is our correct answer. This is the same question. I don't know why it's there twice. So, which of these is the most acidic hydrogen? What do y'all... Well, it already said that the answer is C, so fine. We know that the answer is C, number 3. And why do we like C over the other answer choices? What do y'all think? It's alpha to the carbonyl. Exactly. So what... We have a special name for that position. You guys remember what it's called? This position and this position have special names. What do we call them? They end with -ilic. Yes, so we have the benzylic and the allylic. Okay, so someone had asked, for acidity, how do we know, how do we do it when it has FBr and I with an OH? So do you mean like when you have a chain and there's like an I on it? Or an I and an OH? Like that? So that's less about acidity, I think, and more about... Well, okay, that goes hand in hand. So I'm going to stop myself before I say that. So that has to do with electronegativity. So between FBr and I have to look at a periodic table, but I think iodine is the most electronegative. And so the more electronegative it is, the more acidic the hydrogen will be. And the reason is because the more electronegative it is, the more it pulls on its electrons, and the less tightly it holds on to that hydrogen, so it's easier to steal. So the most electronegative will be the most acidic. You're very welcome. And so yes, the allylic position here is going to be the best, and that is because that is the alpha position, and it's super acidic because of the carbonyl. So yeah, we're pretty much at 250. I don't want to start another question because I want to leave a minute or two for you guys to ask me anything you have. Any questions, comments, concerns, anything? If not, you're free to go. I sent the attendance link one more time just in case. I hope you guys have a great day. I'll stay on for a minute in case you have any questions. You're very welcome. So for racinization, is he only asking those type of questions? Yeah, pretty much. That's really all you can ask for racinization. Have a good one. You had really great questions.